In the last section, we looked at how genetically biased connectivity can improve the learning of associations between hearing phonemes and speaking phonemes. Now, let's look at how learning words is handled in the same architecture, building on the learning of phoneme-related behaviors. There's another type of attention component defined by genetic information that also gets inputs from the phoneme receptive fields. This attention component drives a sequence of behaviors, and again, the first behavior is to prolong the activity corresponding with a phoneme that is heard. But in this case, the component prolongs the different populations corresponding with a sequence of phonemes at different phases of modulation until a pause is heard. Then it synchronizes and releases the outputs to the discriminates words area. There's also genetically defined connectivity from the discriminates words to the activity overlap area, and from the discriminates words area also to the speaking phoneme sequences components. And remember, these speak phoneme sequence components drive more or less randomly selected sequences of speak phoneme behaviors. There's also genetically defined connectivity from the activity overlap area, which goes to reward components and then goes on to from the reward components to target the speak phoneme sequences behaviors. So once again, let's see how the combination of experience and genetic programming interact. Suppose the infant brain hears a word. The sequence of phonemes results in an active column population at the discriminates words level of complexity. This activity targets a range of components corresponding with behaviors of speaking sequences of phonemes, and I've just illustrated one component. Each speak phoneme sequence component targets a set of speak phoneme components and activates them in turn if it's selected. So the speak sequence component will drive speaking its corresponding sequence. So as a result, the infant speaks a sequence of phonemes and therefore hears the sequence. The sequence spoken will be the one that happens to have the largest current recommendation weight from the activated discriminates words columns. Hearing a phoneme sequence just spoken by self leads to activation of columns in the discriminates words area again, but at a different phase of modulation from the population activated in response to hearing the original word. The attention component now synchronizes the two populations and releases them to the activity overlap area, resulting in receptive field detections in that area. And depending on the degree of similarity between the original word and the self-spoken word, the recently selected speak phoneme sequence component will have the weights of its recently active inputs increased or decreased, modulating the probability that the same sequence of phonemes will be spoken in the future in response to hearing the original word. So, just as for phonemes, hearing the word will lead to imitation. If a speak phoneme sequence component always gets negative rewards, it'll be eliminated and its resources recycled. So the effect is to create imitation of words that are heard, and establishment of behavioral sequence components corresponding with each word. Note that one simplification of this model is that in an actual brain, the speak phoneme sequence components could actually be located in the cerebellum rather than the basal ganglia.